Mark your calendars for a special day. The day when an extremely rare starburst illuminates the night sky with bright light is just around the corner. We are all witnessing a new astronomical event that promises to create a new star visible for weeks that will shine brighter than everything else around it. No telescope is needed to witness this cosmic spectacle. You can see nova with your own eyes. Novas are unusual stellar explosions where huge amounts of matter suddenly explode onto the surface of a white dwarf star. This explosion temporarily increases the star's brightness by a factor of 1,500, making it visible as a new star in the night sky for days and weeks. Connoisseurs of the night sky may already be familiar with the constellation Corona Borealis or the Northern Crown. Less experienced astronomers will find the Corona Borealis among the more familiar constellations of Boötes and Hercules. If you see a row of bright stars forming an arc, you are in the right place. A new star appears in this arc after a new event. White dwarfs are not ordinary stars, they are the remnants of our sun-like stars that have used up their nuclear fuel. These stellar bodies are very dense and hot, about the size of Earth but with the mass of the Sun. Because of their enormous density, white dwarfs have a strong gravitational pull that allows them to suck matter away from neighboring stars. A white dwarf can survive for a very long time and slowly cool even without nuclear fusion. In this phase, it behaves strangely, separating matter from its environment. When enough mass accumulates, it triggers a huge explosion. We know this phenomenon from binary systems, where a companion star, often a red giant, reaches the end of its life and loses mass. Compared to a white dwarf, a red giant is larger but less dense and loses mass to its smaller, heavier companion. Hydrogen is mainly extracted, creating a burning mixture on the surface of the white dwarf. In the case of T Coronae Borealis, this mixture explodes approximately every 80 years. The next burst is expected to occur in September 2024, and there is palpable excitement in the scientific community and among stargazers. Although the new event is more than 3,000 light-years away, we can see it as if it were happening live. In fact, we are looking at an event that happened 3,000 years ago, but its light is only now reaching us. At that time, the Iron Age began on Earth, Egyptian culture flourished, and the first cities appeared in Greece. For us, however, the present reality of a nova is when its light reaches our eyes, and telescope. T Coronae Borealis allows us to experience this sight every 80 years or so. Historically, 3 of these innovations are well documented. The oldest report dates back to the 12th century and describes the miraculous appearance of a new star on the Northern Crown. Scientists have been observing the white dwarf T Coronae Borealis intensively for the past few decades and have noticed an increased variation in brightness since 2015 and 2016. These signatures, along with increases in radio and X-ray emission, reflect activity seen before previous eruptions. The last novae in 1866 and 1946 were particularly well documented, giving researchers valuable information for comparison. In 1866, scientists initially thought they were witnessing the birth of a new star. Noted astronomer William Huggins noted nova in Corona Borealis in his notes. About 80 years later, scientists identified the increase in brightness as an explosion in a distant star system. Today, with advanced telescopes and satellites, we can document and observe this cosmic event more precisely than ever before. The new satellites will monitor the 2 stars continuously and record the exact amount of accreting matter and temperature changes on the surface of the white dwarf. These precise measurements allow us to predict when critical mass will be reached and when the expected thermonuclear explosion will occur. This explosion, which is similar to the power of 476 trillion hydrogen bombs, is known as a thermonuclear explosion. It begins with the accumulation of large amounts of hydrogen into the white dwarf, forming a thin layer and eventually accreting around the disk. Gravity pulls this material to the white dwarf's surface, where it compresses and heats it. As more material is collected from the white dwarf, the pressure and temperature increase, forming an explosive mixture. Once the critical mass is reached, the fusion accelerator releases a burst of immeasurable power, increasing the white dwarf's luminosity by a factor of 1,500 or more. The temperature of the white dwarf T Caronae Borealis at the moment of explosion is about 10 million degrees Celsius. In this immense heat, hydrogen atoms fuse into helium, releasing enormous amounts of energy. This fusion process is similar to reactions in the cores of stars, but differs in that the mass is on the surface of a white dwarf. The explosion throws the accreted outer layers into space and creates the primordial new lightning. With the help of satellites and telescopes trained on the white dwarf, we can experience this event with greater accuracy and precision than ever before. The extreme increase in brightness is temporary, but the new one remains visible for days or weeks after the explosion. The white dwarf will gradually return to its normal brightness, allowing observers to watch the slow dimming of this bright point of light each evening. A nova is easily visible to the naked eye, even in areas with significant light pollution, and shines as brightly as Arcturus or Vega at their peak. Over a few days, the brightness will decrease until the star is barely visible without telescopes or binoculars. The whole event is expected to take place in a week or two. If you want to compare, look at the constellation before the new one. During a nova, you can watch the big star gradually burn up. While we humans can see a nova in the Caronae Borealis system every 80 years, the longevity of the T Caronae Borealis show is uncertain. Eventually, the white dwarf will lose its power, either by fading or exploding like the last bright nova. A white dwarf is basically the burned-out core of a star that was not massive enough to go supernova. After stripping away the outer layers, what remains is a compact, dense star composed mostly of carbon and oxygen. These stars cannot produce energy through nuclear fusion and gradually cool down. But their immense gravity allows them to extract matter from their environment, causing repeated nova explosions over thousands or millions of years. Once a white dwarf crosses the Chandrasekhar limit, which is about 1.4 solar masses, it can no longer remain stable. It collapses under its own gravity, resulting in a spectacular Type 1a supernova. This supernova outshine all the stars in the galaxy combined, leaving behind a black hole or neutron star. As we eagerly await this next nova, be sure to keep an eye on the night sky and the constellation Corona Borealis. This rare event offers a unique opportunity to witness the birth of a new star. Stay tuned for more updates and don't miss your chance to be a part of this extraordinary cosmic event.